All right, let's get on to section 5.1 here. I've got some, I think it's an interesting kind of presentation. It doesn't quite come from the book. Our text, it does have, they do have some good material in the text, but I like this one particular presentation that I've got from a previous text that I taught from, and I'm wanting to just get it across to you now. So what I'm going to do is go to my iPad, and let's go in, and I want to draw a couple of diagrams for you. First of all, what what does what does area under a curve mean? You know, what does it do for you? And we're talking integration here and antiderivatives and the combination of things. Let's pull some items together here. I think this will be a starting approach in a certain way. Let me say this. This first, I'm going to go start up here on this front top right um, diagram. And if we were talking about, if it was in a vehicle or some type of traveling that was moving along at a velocity of 30 feet per second, you got feet per second velocity on the y-axis and time on the x. And if every 2 seconds I checked it and I was going 30 feet per second for an entire 8 seconds, the distance traveled from start to finish. I'm moving at time zero, and for 8 seconds, I'm continuing moving. So it ends up that this area under here would actually be what? That's what we're looking for right here. What is that? Right. Well, it's a matter of recognizing that area that we're talking about under the curve, it's a very straight line, but we'll call it a curve, and you'll hear that referred to in straight lines also. It's a curve, a straight curve. But the idea that the distance is equal to the velocity, 30 feet per second, times the time, which is 8 seconds, and you see that you end up with 240 feet. So it's actually so if there was a graph that didn't have the side and all the shading that I have here, if it was just this line, the area under the curve between the curve and the x-axis would actually be the distance traveled. If it's a velocity function going across there, it's the distance traveled. We'll talk more about that in a little bit. So one of the situations is if it's constant the entire time, then you can tell quickly what the measurement is. But if we've got a situation over here, look at this velocity on the one on the left here. If I'm starting at time zero, it's going 20 feet per second. And this is every 2 seconds I check it, okay? Every 2 seconds I check the velocity, and at 2 seconds I'm going 30 feet per second, and 38 after 4, and at 4, and 44, and 48, and 50. How far did I actually travel? Well, the area under the curve we know is the distance, but this has got an unevenness and it's not regular at all. So a way of demonstrating how you can look at this in such a way and get benefit from it, and coming into calculus now, is how do you find the area under the curve? How do you find the distance traveled given this type of information? Well, one of the ways is this. If we were to take, over here, this was rectangles, length times width, and that gave us an area. Well, if we were able to break this up into small rectangles, we could do a summation of those areas of those rectangles and calculate the distance. And so in this situation, let's aim low. So we're going to aim low on the low side of this. First 2 seconds, we went from 20 feet per second to 30 feet per second. Let's say we went 20 the whole way. How far would that have been? Okay. And then from this point over, we're going to hit the bottom every time. So 30 in the 2 to 4 second interval, we're going to say we just went 30 feet per second for the entire time. Okay. So we've got rectangles that are forming from this, and the total area is definitely going to be less than the actual distance traveled because every one of them is low. Every one of them is short of the actual arrangement. And how far would that be? Well, let's take a look at this. So we would have it would be the area under this, each of these rectangles added up. So we would have the distance traveled is equal to 20 times 2 plus 30 times 2 plus 38 times 2 plus 44 times 2 plus 48 times 2. You could factor a 2 out and just add up those numbers. Let's just add them together kind of quickly here. You got 40 plus 60 plus 76 plus 88 plus 96. That's 176. That's 264. 270, 360. So that's a 360 feet total if we did it at the low end of each interval. Now let's check out this. What if we did the high end of each interval? Okay, let's check this out now. What would we get if we did the high end of each interval? Well, let's take a look at that. All right, well, that means that the first 2 seconds, if we said we did 30 the whole time, okay, that would be one thing. And then the area would be, you can take it be higher. It would definitely be more than. And for the second one, let's pick 38 the whole time, and 44 the whole time, and 48 the whole time, and 50 the whole time. All right. As a result, then we would end up with, if we measure this, check this out. So this is the low distance. We know it's low. The lower distance is called that. It's less than the actual distance. Let's go to the higher distance. What's the higher distance? The higher distance, this time I'm going to add up the numbers and multiply it times 2. All of them are multiplied by 2. But this time we've got 30 plus 38 plus 44 plus 48 plus 50. All right, and that gives us 80, 118, 162, 210, that's 420. 2 times 210 equals 420. So the higher distance that we measured on those intervals would be 420, all right? And so the difference in between, notice the lowest starts at 20, and the highest goes to 50. And this interval is too wide, and the difference between 20 and 50 is 30, okay? So there's a difference between the low and the high. We know we're above and we know we're below, but it's 60 feet difference that we've got going there, right? 60 feet variation in between the two numbers. Well, take a look now. What if we just said, what if we broke it down into every second? The same values in the situation is what we're looking at. So we're still looking at this same graph, but this time we're going to break it into 1 second intervals. So I go to the bottom of the 1 second, 20 over. I'm not even sure what this value is exactly, because it's not exactly proportional type. It's a variation of the curve type thing. But then every second, I'm measuring how far we went. Again, we know we're low, right? We're low because every time I'm starting at the bottom end of the interval, the lowest point that we went in that interval, the slowest point in every interval, right? And this time, instead of doing the calculation, what I'm going to do is, well, look at the difference from the high, okay? So high at 1 second will be up here, then it's here, here. So notice that the box that I'm drawing between the top, the high, and the low guess, it's smaller this time, all right? Each box is smaller. But notice that the height is still the same because we're starting at 20 over here, we're starting at 20, and we're going up to 50. But this time, it's only 1 inch wide. So this is 30, and this is 1. So there's a difference of 30 feet between the high and the low in that situation, whatever that circumstance tends to be. Yeah, okay, and the main idea I'm trying to get across is that, okay, if we went to a half a second, then it'd be a half times 30 would be the difference. And then a quarter, and then a tenth, and 100th. And as that limit, what we're calling delta t for time, delta t started at 2 seconds, went to 1, went to half. So it's getting, as it goes to zero, as the limit goes to zero, it ends out that this thing totally smooths out, and we end up with the area under the curve actually no rectangles at all. It's the rectangles are so narrow that they don't appear to be rectangles. It's just smooth. It's a smooth curve, and the area under the curve. So as it goes to zero, it does that. So as a result, the main idea is the area under the curve is the distance traveled. So if I have, let's go over, so that's the main idea. Area under the curve is the distance traveled. And we're a velocity function. When the velocity function starts like this, the area under the curve is how far it actually traveled. That's the main idea. So check this out. So the idea is that if we were on a bike or something and started at zero this time, we didn't start moving, we started at zero, and we continually increased regularly up to, and after 3 seconds, we were going 15 feet per second, then the distance we travel is equal to the area under this curve. And the area of a triangle, we know is area equals 1/2 base times height. Base times height. So that's equal to 1/2 the base is 3 seconds, and we did it in 3 seconds, and then the height was actually 15. So we end up with 45/2, or 22.5 seconds would be, in the formula, notice what this is. This graph would be the rate of change from this point to this point. Change of y is 15, change of x is 3. This is 5. This is 5t. Okay, this is t down here in time. This is velocity. All right. Well, the formula would be 5t. And notice we're going to talk very shortly about antidifferentiation, finding the area as a result of knowing the function and taking the antiderivative. We'll talk about that a little bit more in coming seconds, okay? So be well and be looking. There's another section coming up about some other problems that I want to discuss from section 5.1 and others related to the end of 4.8 as well. So we'll be doing that really soon, and I hope to talk to you shortly. Make sure you keep stepping forward on the sapling problems. Okay, before I get too far from this diagram, let me say also that some of the problems in the text that are in sapling are similar to the diagrams that I've drawn here. The one I said, I called it from the left-hand side, was the low side. So it was because the curve is going up, the low side is on the left over here, right here. I'm showing the top diagram here. The low side for the second is here. It's on the left. It's on the left. It's on the left. So sometimes the high and the low, I was referring to high because it was the upper one and the low was the other one. Well, sometimes the text breaks it down into left and right. They say the right area, the right estimate of the area. And the right, in this case, would be the high of the one that we're doing here. Because the curve is going up, the right-hand side is the high. The right side of the interval is the high each time. So the right of this is the high end, okay? So when I was referring to high, there's a couple of problems that say do a left area, a left side area, or a right side. And that same, get the logic of it. If the curve was looking like this and the curve was going down, notice the left side would be the high. If I have an interval here, the left side is above, the left side would be above the whole time. And the right side would be below. In contrast, because the curve's going down, right and left vary on what's high and what's low. So read the picture and get the picture of what they're talking about in the text. And then when they give a problem and talk about right or left, get the visual on it. And it's the same thing that I'm calling high and low. Okay? So make sure you're conscious of that when you're reading through the problems. And some of those problems, it's kind of interesting to see it. And when we're in a little while, we're going to be getting the area under the curve to get even more meaning for antiderivatives um, and integration. Okay, so that's coming soon. And keep going with the problems in sapling.